Hello there, my name is Thomas. I'm representing investmentexcel.com in today's session, where I will give you a brief introduction to linear regression's more flexible counterpart, the nonlinear regression. I will implement the model on a time series of stock returns as a simple function of time. And as we normally assume, there is somehow an exponential relationship between time and a stock return due to earnings growth being linked in some in some scale to underlying growth in economic fundamentals like GDP. We will use the ordinary least squares estimation technique, where we ultimately minimize the sum of squared residuals between the actual observed price of the stock and the model predicted price squared. Alright, this topic is slightly advanced, so please refer to other sessions I have made on regression and OLS estimation. Let's take a look at a very simple data time series, 25 observations, and just to bring in some reality, I assume that these are years, and then we have the stock price, and perhaps you can see some kind of, at least not linearity. So a model that is more flexible in the functionality than the linear relationship as we have in simple regression and simple multiple regression is warranted. Here we have time, and time of course just reflects the observation structure of years. And over here, just to start with a simple graphical description of the stock price evolution, you clearly see a exponential tendency, and the idea now is to identify the trend, the exponential trend. And this can be done by the non-linear regression technique. So we build a functional relationship that takes into account the supposed exponential relationship in the actual time series, and then we fit. And the model I use is this one. So I assume a true model of the stock price governed by this exponential relationship with a constant times the exponential function raised in beta 1 times xt, and xt is simply the time at time t. So if t is equal to 8, it's 8, and here's the noise. For now it's just a normally distributed variable, but we will not in this presentation dig too much into the statistical inference of the model, but primarily look at the fitting capability in the OLS technique. So as always, when we try to fit, we start by building the functionality that we have assumed, and in this case it looks like this. So a beta 0 times the exponential function where you have beta 1 this parameter in the exponential function times multiplied by the time. And if you're not that accustomed to regression building and regression modeling in general, then please note that the error term has cancelled out, because what we estimate is not the actual price, it's the expected price. As long as we are operating with a sample, as we assume this is taken from a real true world, a population, then we have to estimate the expected value, because there is statistical uncertainty. And this I do all the way, and I'll just put in some other values because those values were the correct values. And here is the OLS technique. For each observation, we take the difference between the stock price and the model stock price, and we remember to square it to avoid any netting out of negative and positive numbers, which would essentially leave us with a lower error term, or a better model if you like. And I do that all the way down, and then I sum them. So here's what we call the residual sum of squares, RSS, and this is the number that we now have to minimize. And we minimize them, we minimize the expression by changing the estimates in the model. So the idea now is to use an algorithm, which is the solver algorithm in Excel, that gradually changes these values until it finds the lowest possible value. The lowest possible value is the value associated with the best model, as the distance between the stock price and the model's predicted price is the lowest on average. Okay, as I said, we use the solver, and the solver you will find in the data category, unless you haven't downloaded it in the add-in function in file. Just show you, we have an add-in, and here's a solver, and this solver is not in the active application add-in as default, so you have to activate it. Also, if you like to have all the nice regression tools and so on, you have to activate the analysis toolpack and also the VBA analysis toolpack. Okay, I'll just cancel it because obviously I have it up here. Set the objective function. This is the function that Excel would like to do something with, as you decide, and you can either max, minimize, or enter a specific value. We'd like to minimize, and we'd like to minimize it with respect to these two variables, beta 1 and beta 0, and we have no constraints. So I found a solution. So now the model is estimated and is represented by the blue. So now this model, it's nice and it looks good and it's a trend, but But remember what the purpose is. The purpose is to use the model to extrapolate in the future a value for the stock price. We don't do this just because it looks good. We want to use it to extrapolate. So assuming that all statistical properties are okay, as I said, we'll not go into it here, we can take the model and put in the time value somewhere in the future, and we will have an idea of what the price is. So for instance, I would like to know what the price is in year 30. In year 30. In this case, I will take the model times this value, which can be interpreted as a annual percentage. So the stock increases by 16% a year times 30. So you see that there is a dramatic increase here and in 5 years forward. And that's because of the exponentiality. Let's just type in 25 and see if we hit 29. Or at least approximately. That will show it's of course correct. So this is the way to do it, and of course you could just go 1 year ahead, but just remember that this is taken from year 0. You could make your own starting point by using, say this is now at the end of year 25. We start by this, and then we just move forward with 16% a year. Nonlinear regression is used everywhere in business and in academics, because it has the flexibility to fit all sorts of graphical representations. So it's very efficient, and in Excel it's quite easy to estimate any functional relationship. It could be a square root model, it could be a polynomial model, it could be cosinus, sinus, it could be every model. With the OLS technique, you can do it in exactly the same way as this. The only thing one should be aware of is the statistical interpolation. But in terms of just being able to fit, the idea is exactly the same. All right. Thank you very much.